Metabolism is a term that we use in everyday conversation, usually when we're talking about losing weight or gaining weight or that kind of thing, right? Someone will say, "Oh, I have a slow metabolism. I can't eat any of that cake in the office for Ted's birthday because it'll all go straight to my thighs. It'll go right around my waist or something like that because I have a slow metabolism." Or my brother, such a fast metabolism, eat whatever he wants and it just doesn't gain a pound. I'm so jealous of that fast metabolism. So we know something about metabolism. We know it has something to do with the food we intake and how we store that energy. But that's not all it's about. That's a little piece of it. Metabolism is all of the chemical reactions which take place inside of our cells, and the energy processing reactions are one part of that. Now, obviously, we do not have time in one unit of a single semester general biology course to talk about every single chemical reaction that takes place inside your body. So we're going to zero in on just a couple of things. We're going to spend a lot of time talking about photosynthesis. We're going to spend a lot of time talking about cellular respiration. And we're going to talk a lot about enzymes in this unit as well, because every metabolic process in your cells is going to be catalyzed by enzymes. So even though we can't talk about every individual chemical reaction, we actually can, in a way, touch on all of them because we're going to talk about enzymes in general, and all of them have enzymes involved in the process. So pictured here in front of you, you see a koala bear, and she is eating some eucalyptus leaves. So we can actually see two processes occurring simultaneously. One, the eucalyptus tree is doing photosynthesis. That's why the leaves are green, because there are chloroplasts inside those leaves, and those chloroplasts contain chlorophyll, so that's capturing light energy. And through mechanisms that we're about to study, that light energy is going to be stored as chemical energy inside sugar. So that's photosynthesis. But then that sugar, it's the eucalyptus wants to use the sugars for itself. It wants to use it to make more cellulose, to build more plant material, or it wants to store it as starch so it can use it for its own energy purposes later on. But that koala bear would very much like to use the sugar as well. So it's going to eat that sugar, and it needs to get that energy back out of it. So it's going to use the oxygen that it's breathing in from the environment. And that oxygen, where that oxygen came from, that comes from photosynthesis as well. Oxygen is a byproduct of photosynthesis. It's going to breathe in oxygen, and it's going to eat the sugars in the plant, and it's going to bring them together through cellular respiration, and it's going to use that to unleash that chemical energy and use that energy inside of its cells in order to power climbing around trees and doing koala bear type things, right? So we have both kinds of metabolic processes that we're going to study in depth on display here in this one little GIF. But alas, I am getting ahead of myself. Before we can talk about photosynthesis or cellular respiration specifically, we need to talk about energy as a general concept. So energy is the capacity to do work. Work is the ability to move things around, to change a system. There are different kinds of energy. You can have the energy of motion, to move things around. That's what we call kinetic energy, energy associated with motion. And you can have energy like heat energy, thermal energy, and that's actually just a kind of kinetic energy in a way, because the molecules inside of a solid object, as they start getting more and more energy added to them, more thermal energy, those molecules start vibrating faster and faster. They start moving more and more. The bonds start vibrating and wobbling a little bit faster and faster. So they start moving with more randomness and more energy to them. And that's what we kind of detect as heat. That's what increases in temperature. So heat is a kind of energy that we can talk about as well. We can talk about potential energy, which is stored energy. And you can talk about converting one form of energy to another. So if, for example, we were to push a ball up a hill, while it's moving, that ball has kinetic energy. It's got energy of motion. But that ball is going to slow down as it rolls up that hill. Is the energy disappearing? No, energy really doesn't disappear. It can only be converted from one form to another. It can't really be destroyed. What's happening is as the energy is disappearing in kinetic form, it's changing to potential energy. Potential energy is stored energy, energy that matter possesses because of its location or its structure. So at the top of the hill, there's no more motion in that ball. It'll pause at the top of that hill because it's filled with potential energy. And then you can convert that energy back to kinetic energy by giving it a little push, and it rolls back down the hill, doesn't it? So you can convert all of that potential energy back to kinetic energy. We use this to our advantage in hydroelectric dams all the time. We store energy in water by just trapping it behind a dam, right? It's uphill of the dam. It's a little bit above it, and it wants to fall down. It's filled with potential energy, that water, because of its position, because it's uphill of where it would like to be. And we allow it to fall down. We convert that potential energy to kinetic energy by just allowing it to flow, and we capture that kinetic energy and convert it to electricity, to electrical energy in the process. Okay, so we can not only convert things from potential energy to kinetic energy, in the process of doing that conversion, we can capture some electricity for ourselves as well, which is similar to something we're going to do in metabolism. So we have potential energy, and a kind of potential energy that we can have is chemical potential energy. So because of the structure of certain molecules, they can have energy stored, we say, in the bonds. That's kind of a shorthand. It's kind of a term of convenience. But it's because of the structure of the way that the chemical is put together that it has more energy when it's put together that way. And sugars, which are in ring structures, are in high potential energy states. So we can get a lot of energy when we break down sugars that we wouldn't get from other types of molecules. So sugars have a lot of potential chemical energy inside of them. All right, let's move on to the next slide. Now I've done it. I started talking about energy, and now the laws of thermodynamics have found me. Well, it was inevitable. So let's talk about the first couple of laws of thermodynamics. Now, a law, we talked about a hypothesis in science, which is kind of an educated guess to explain a narrow set of observations. We talked about a theory, which is a model which explains a broad set of observations and is usually backed up by a mountain of evidence. A scientific law, on the other hand, is something that appears to be, as near as we can figure, an unbreakable rule of the universe. It is one of the laws of reality. If you run an experiment and it appears to violate one of the scientific laws, like the law of thermodynamics, probably there's something wrong with your experiment, not something wrong with the laws. I don't know if any of you were reading scientific articles a few years ago when they thought they found neutrinos traveling faster than light, but that would have violated a scientific law that says no particle with mass can travel faster than light. Everyone was freaking out when that happened. It turned out there was a loose cable in their detection system, and that's why they got that result. So laws are things that are quite important in science. So let's take a look at these laws of thermodynamics. The first law of thermodynamics says that the energy of the universe is constant. Energy can be transferred. Energy can be transformed, but it cannot be created, and energy cannot be destroyed. What does that mean? That means when I get all of my firewood and I start a fire and I get all this nice heat energy coming off that fire, I didn't create that heat energy. The energy in that fire was always there. It was stored as chemical energy inside of that wood, and I just converted it. I catalyzed a chemical reaction that's converting the chemical energy into thermal energy and light energy that there is. And the amount of chemical energy that was in the wood is equal to the amount of light and heat energy that's being released and the amount of chemical energy that's left over in the wood, in the ashes and charcoal that will be left over at the end. Whatever you had at the beginning, you will end up with at the end. Okay, so you can't create energy and you can't destroy energy. You can only transform it from one version to another version. And the same thing is true in biology. This bear is getting chemical energy from the food that it eats, right? So it eats this salmon, And then as it processes that energy, what happens to that chemical energy? Well, some of that energy is going to move its muscles. So it's converting that chemical energy into kinetic energy to move itself through the water, to hunt, to run, to be able to pump its heart, to move fluids through its body, to be able to gnaw its teeth and move its eyes around and fire axons in its brain, right? To be able to think and feel and do all these kind of great animal things. But some of it's being converted over to heat, right? It's venting heat the entire time as well. What's happening to all of the chemicals that are inside that fish, right? It's made out of material, right? It's made out of atoms. Well, that's being converted over to other products as well. It's breathing out CO2 and water the whole time. Same chemical constituents that you would find in most organic molecules. Not only can energy not be created or destroyed, matter can't be created or destroyed either. So both of these, this is the law of conservation of energy and matter when you take them together like that. Now that brings us into the second law of thermodynamics, and I am going to try very hard to keep my thoughts on this to a minimum because I love talking about this topic. The second law of thermodynamics states that during every energy transfer or transformation, some energy is unusable and is often lost as heat. Heat is low-quality energy. You can't do a lot of useful work with heat. And I know what you're thinking, hey, don't we run like steam engines and things off heat? Surely we could do a lot of useful work with heat. Doesn't a nuclear reactor just generate heat? Don't we use heat all the time? It's the conversion of other forms of energy into heat. It's having that kind of source of high-quality energy and converting it into other forms. That is what allows you to create a very concentrated central location of heat. And it is having that strong source of heat and an environment which is much cooler that creates a flow, and then you're able to harvest energy from that flow. But just regular heat out in the environment, not so much. And then after that, it has the second clause which says every energy transfer or transformation increases the entropy of the universe. What the heck is entropy? Usually, the common answer you'll get is that it's a measurement of how disorderly a system is, how much chaos there is in a system. So since energy can be transformed and transferred, and every transfer only increases the entropy of the universe, well, that means that the overall entropy of the universe has to always be going up. So what this tells us is that the overall disorder of the universe is always going up, and people make all kinds of philosophical conclusions about that. And I think this idea that it's disorder and chaos, it's not a bad way to think about it. It's really not, but it leads to some slightly inaccurate intuitions about entropy. Entropy is kind of an tendency for systems to want to return to a stable state. As it turns out, a highly ordered state is fundamentally unstable. Because what do we think about as being orderly? If I were to have a whole bunch of marbles and I just let them spread all over the place, right? I just drop them all over the floor. That's not very orderly, but it is stable. Like they're not going to go, they're just wherever they want to be, right? That's where they would naturally fall. That's a state of high entropy and very stable at the same time. I say that this is a stable state because no matter how we mix up the marbles on the floor, you can mix them one way, mix them another way, mix, there is an infinite number of arrangements of messy marbles on the floor that we would say, okay, they are in the high entropy, messy, spread out state on the floor. So no matter how you mix them around, they are going to remain in that state. Hence, it is stable, right? It would take a lot of work to get them out of this configuration, which we call the high entropy state. However, there's a very small number of arrangements which we would call a highly ordered, right? If I were to stack them all up like they were a crystal, or I would arrange them into rows and columns or something like that, that would be a highly ordered state, and I would have to do a substantial amount of work to get them into that arrangement. any amount of, like, if there was like a little earthquake or something like that shook up the room, it would then push them back into the high entropy disorderly state. So a state of high entropy is the natural tendency for every system to wish to return to, because being orderly takes work. Meanwhile, if I were to gather them all up and put them in a container and put that container up on a shelf, well, I've just put a lot of potential energy into that system, right? I've just added a whole bunch of energy to get them into that orderly state. So I've decreased the entropy of the system by adding energy to the system. You see the kind of connection there? And if we take a look at other kinds of systems, if we take a look at this diver up on the diving board, he added energy to himself by climbing up on that diving board. And spontaneous change can occur to this system by just stepping off the diving board. What's his preferred stable state? Well, it would be down, right? That will be where he's more stable. That's where the spontaneous change will drive him. So he's going to lose all that potential energy. It's going to be converted to kinetic, and he will arrive at a more stable condition down in the water. If we have molecules, remember when we were talking about diffusion, if we have a whole bunch of molecules that are clustered together, that's a highly ordered state, low entropy, but molecules move around randomly, right? So they are going to start bouncing around. They're going to want to spread out. A state of high spread is a high entropy state. It's very stable. A state of clustering is unstable and low entropy. It's highly ordered, right? So the tendency to spread out is entropy in action. And we would call this disorderly, but you can see how it's not quite a perfect analogy to just call it chaos or disorder. And same thing here, a highly structured molecule like sugar, well, this is a very orderly structure. And there's a lot of energy in this structure. You have to put in energy in order to get molecules to connect to each other like this. So we say that there's energy stored inside this system, stored inside these bonds. It's a shorthand for saying that this is a structure of high potential energy. And that energy is released when we break it down into simpler components, carbon dioxide and water. So systems which contain large amounts of energy are unstable, and entropy increases when they reach a more stable state, and that will occur spontaneously if we give them a little bit of a push sometimes. Sometimes they need a little bit of a push. We call that activation energy. That might be pushing the diver off the diving board or giving the right kick to help this sugar come loose. A spontaneous change in a system occurs if the result of that change is more stable. In other words, if it loses energy. Now, I can already hear you thinking, wait a minute, this makes sense. This makes a little bit of sense, right? Things would rather be in a stable state. It's more likely for things to just sort of like fall onto the ground than stay up on a shelf or something like that. If like things wouldn't just be sitting on the floor and then fall onto a shelf into a more orderly state, that would be silly. But what about cells and living things? They're highly ordered structures. If things spontaneously break down into simpler components, don't like living things and cells and human beings and proteins, which are big complicated structures, doesn't that kind of break one of these laws of the universe that you just said are unbreakable principles of reality? How does that work? It doesn't break the laws because we have a source of energy constantly putting more and more and more power into the system. We have the sun that is in a perpetual state of increasing the amount of potential energy we have available to us. So it is true that organisms are highly ordered systems. However, in order to get that complexity, cells and organisms in general have to convert high quality energy, sunlight, into low quality energy, heat. That's what you emit all the time, right? Through your body heat is just heat. And how do we convert it? Well, plants convert sunlight into chemical energy. We eat the plants. We convert those sugars into heat energy, and we send that out that eventually radiates back out into space. So life on Earth actually increases the rate at which that high quality energy ends up as low quality energy. In the grand scheme of things, life on Earth is accelerating the pace at which things fall into entropy, even though for a brief time here in the life cycle, entropy decreases in living things. It's kind of beautiful. The net effect on the universe is still an increase in entropy. Energy flows through living things, while chemicals cycle round and round and round ecosystems.